Okay, we have two types of formulas that you see on reagent bottles when you're in the lab, and one of them is an empirical formula and one is a molecular formula. Honestly, to me, the most important one is the molecular formula, and you'll see why here in a second. But an empirical formula is the smallest whole number ratio of atoms present in a compound. Okay, so if we look at hydrogen peroxide, for instance, so its actual true molecular formula is H2O2. Okay, but its empirical formula, so you take the smallest whole number, so you have 2 would be your smallest whole number there. Okay, and if you write out the simplest form, you would just have HO. So you just have hydrogen, oxygen. Okay, a molecular formula is actually the true number, the actual number of atoms or numbers of atoms of each element present in a molecule. Okay, so if we look here, so for instance, ethene, C2H4, that's actually how many carbons and hydrogens ethene, the compound, has. Okay, and pentene, the same, and then hydrogen peroxide, so I use that again here because this would be its true molecular formula. Okay, so let's go through and think about what the empirical formula for these three would be. Okay, so if we look at ethene, for example, where am I lost my... Okay. Okay, so we're given the molecular formula, and we're going to see how we can derive these as well. That's what we're going to get to. But first we have to know which one is which. Okay, so we have our molecular formula, and now we want to write out the empirical formula. So if we were to look at ethene, C2H4, okay, what do you guys think the empirical formula would be? What's our smallest whole number ratio there? Okay, exactly. So we would have and we already have seen that peroxide is this. Okay, what about for pentene? Okay, so we've got 5 would be our smallest whole number ratio, right? So 5 into 5 and 5 into 10, we get CH2. Okay, the reason that I chose these two as an example is if I'm in the lab and I go pick up a bottle and all it says on there is CH2, is that really telling me a whole lot? Is that telling me exactly what compound I have? Okay, so as you can tell, I don't really like empirical formulas. I think they're kind of pointless, but from the empirical formula, we can actually derive the molecular formula. So that's what we're going to see. Okay, because CH2 really tells me nothing. There are, hundreds of compounds that can be broken down into a simpler formula of CH2. So that doesn't really, and they all have different properties and they have different, there's different side effects to these as well when you're handling them. And so for a molecular formula, it actually tells you exactly what you're given. So yes. You're going to see here in a second, you can derive your empirical formula, and then from that, we can come up with our molecular formula. Okay, so yeah. Okay. All right, so that's just showing you also for peroxide, so OH, okay, a lot of other compounds can be broken down into a simpler formula of OH as well. That really, all that tells me, honestly, that looks like an alcohol to me. So when you pick up a reagent bottle, I encourage you in the lab, if you look at one, usually you'll see both, okay, but really the main one that you want to be sure to see is your molecular formula. Okay, so how we determine empirical and molecular formulas is experimentally. So you're actually going to do this in the lab the next time we're in the lab. You're going to determine the formula of magnesium oxide, okay, which most of you probably know can predict what it should be, right? Because we know that magnesium wants to lose 2 electrons, oxygen wants to gain 2. Okay, so you're going to end up with a 1-to-1 ratio. Okay, but there are compounds that we haven't looked at. So those are our group A elements that we've been looking at that we can predict, okay? But we're going to go through and say you have an unknown compound, okay? You want to experimentally figure out what the composition of this compound is, and you want to derive its formula. Okay, so that's what we're going to look at now. Okay, so one way that the empirical formula and molecular formula is figured out is by the percent composition and by doing this experimentally. So here's of course they all can look a little bit different, but this is kind of our reaction vessel here. And basically you submit your sample into this tube here that is heated. Okay, so basically you're determining the percent composition by combustion. Okay, so you're going to heat it, you're going to stream in oxygen into the tube. Okay, and the sample is going to combust. Okay, when it does this, the water, okay, so a combustion reaction, what you're going to produce is CO2 and water. Okay, and so it's going to be absorbed into these areas here. Okay, and from this, so as you can relate the masses and the percentage of the carbon and the hydrogen that are present here, that are absorbed, and you can relate this back to your original sample. Okay, and so you would obviously need to know the mass of this original sample and be able to do the calculations from that point to figure out the amount of oxygen or carbon that is absorbed. Okay, so from the experiment, so we don't have as fancy of a nice little combustion system. We don't really combust anything in our labs for obvious reasons. So, but we are going to do something similar. So you'll see that in lab. Okay, but so from this right here, we're given this data. Okay, this is what I want you to see, that this data here that's given has to be determined experimentally. Okay, so yes, it's being given to you, but someone had to determine this experimentally, like on the previous slide. Okay, so we're given that, this is a lot here, we're going to walk through each step. Okay, we're given that from that experiment, they found that the compound is 24.74% potassium, okay, it's 34.76 manganese, and 40.5 of oxygen by mass. Okay, a percentage just means that it's some part out of 100. Okay, so we can assume, this is one thing that gets students sometimes, that these percentages, we could assume that out of 100 grams of whatever this sample is, that 24.74% is potassium and etc. there. Okay, but we can also convert that percentage and just say that we have 24.74 grams as well. Okay, does everybody see that? That throws people off on the exam. Okay, and the reason we can do that is because all of our numbers add up to 100. Okay, so this percentage is means it's out of 100. Okay, so the first thing we're going to do is we want to come up with a formula. So you're just given this percentage, someone's done this experiment, and they say, this is what we found. This was what was absorbed. This is what we calculated as our percentage, okay, of each of the components. Okay, so the first thing you're going to do is you're going to take each of those percentages, and assuming that you know that you can use them as grams, and you're going to convert to moles, just like we did earlier in Chapter 2. Okay, so you go to the periodic table, and you look up the atomic weight for potassium, manganese, and oxygen. Okay, and so if we look here, we've got our grams are going to cancel. Every time that we go to the periodic table to look at the atomic weight, we know that that is based on 1 mole always, right? So we always have the 1 mole in the numerator there. Okay, so that will be your first step in deriving a formula. You're going to take the grams, convert to moles. So your units cancel, grams cancel, we have moles of manganese, moles of potassium, and moles of oxygen. Okay, does everybody see how we get moles for each of these atoms here? Okay, it's just one single step. Okay, now we want to come up with our formula, okay, which is a ratio of how many atoms do we have of, so what we're really looking for here is we have potassium, an X number of atoms, we have manganese, we have an X number of atoms, and oxygen with X number of atoms. So we're looking for the ratio. How many atoms do we have of each type? Okay, so what you're going to do is you're going to go find your smallest number. Okay, so your smallest number, here we've got two numbers that are both the same, so it doesn't matter which one you choose. And you're going to divide all of your moles by that number, okay, by the smallest number. So that's what's done here. I'm going to show it up here. Okay, so that's going to obviously equal 1. And no, it'll happen a lot because a lot of times in your compounds you'll have one atom of each. Yeah. Okay, and if we divide 2.531 by 0.6327, okay, we end up with 4. Okay, so basically you're just dividing by the smallest number, and this is giving you your smallest, taking your smallest whole number ratio, and you're solving for the number of atoms. Okay, so we look down here at our formula. So we have 1 atom potassium, 1 manganese, and 4 oxygen. So we just plug that in. So now we have an understood 1 there. And this is actually called potassium permanganate. It's the name of this compound. You guys don't have to name that complicated of stuff yet. So, okay, so we get KMNO4. Okay, so we experimentally were given these percentages. Okay, and like I said, you guys will do this in the lab, just in a different way. You will be heating. It will be very similar. Okay, and then you convert to moles. You take each of your masses there and convert to moles, and then you divide by the smallest ratio, whole number ratio, and that gives you the ratio. So you came up with your empirical formula. Okay, here, this is our empirical formula. Okay, it is also our molecular formula. Okay, sometimes they are equal to each other. Okay, so the smallest number here, we have a 1, 1, and 4. Okay, we can't reduce that anymore, right? So our empirical formula is also the molecular formula here. Okay, I want you to try this one. You're going to come up with, so first thing you're going to do, so here you're given the mass. Okay, so you can be given the mass or you can be given the percentage, same thing. Okay, it looks like you have two types of atoms. You have cobalt and you have oxygen. Okay, and I want you to come up with the empirical formula. Be sure you've got your periodic table out so you can look up the atomic weight. This one is a little bit different just because it doesn't come out to be a perfect whole number at the end. And we all know, hopefully I've never seen a formula that has, an atom CO1 or cobalt 1, oxygen 1.3. Okay, we just can't have fractions. We have to turn those into whole numbers. Okay, so the first thing that you did is you're going to convert from grams to moles, using the periodic table and grams to moles here. So we just have two different atoms. Okay, and we take our smallest number. So we divide by our smallest number, which is obvious. We're going to get 1 here. Okay, and when we divide into the moles of oxygen, we get 1.333. Okay. So what we have to do is we have to turn this into a whole number. So I personally, when I have 1.3 and it comes out to that, then I just go ahead and I just multiply it again and again until I see that I get a whole number. Okay, so you would take 1.3, and so it takes 3 times that to get to a whole number. Okay, if you get like 3.99999, you can round that up. Okay, so anywhere really even 3.9 or 2.9, you can go ahead and round those up. And on your exam, there won't be any question there. Okay, once you multiply or whatever, you'll get the whole number. Okay, so if you have to multiply 1.3 times 3 to get a whole number, then you also have to multiply your cobalt as well. Okay, so we just had 1 cobalt, so you have to multiply times 3 as well. Okay, so you end up with cobalt 3, oxygen 4. Okay, so I told you we were going to get to the molecular formula because this is it is the most important majority of the time. However, we just saw examples where the empirical formula was also the same as the molecular formula. So there was no more small whole number ratios that we could divide through by. Okay, but what I want you to do, and I teach it this way, and some students kind of figure out their own way, but I teach it this way because I feel like on the exam, if you can at least do the first part, you'll get some credit if you can't do the last part. Okay, so if you it's just, I see the students get more credit doing it the way that I'm going to show. Okay, because all you're going to do is I'm asking you for a molecular formula. So the first thing I want you to do is find the empirical formula. Okay, so you can at least get the points for that. And then we'll find the molecular formula. Okay, so I want you to take these percentages. You just have carbon and hydrogen. And don't worry right now with molar mass, unless you already know how to do this. You've already studied it. Okay, and I want you just to find the empirical formula first. Yes? Okay, because you got a fraction. So you got 1.3, so you can't have a fraction in your formula. So if you take 1.3 times 3, you get a whole number. So you have to keep multiplying until you get a whole number. For the last problem? Cobalt 3, oxygen 4. Do what now? Yep, you get your answer is 4. Yep. That's weird. Okay, so work on this one. Find the empirical formula first. Is everybody with me to this point? Find your moles. Okay, now what's our next step? Yep, divide by the smallest number. All right, so if we write out our empirical formula, we get CH2. If we go back to the problem, so we have to be given sufficient information here. So our molar mass for this compound is supposed to be 56.1. Okay, so I want you to calculate what's your molar mass for CH2. Remember we add up our molecular weight, talked about molecular weight, formula weight, molar mass. You just add up the number of atoms, multiply it times the atomic weight on the periodic table. Okay, so carbon has an atomic weight of 12.01, hydrogen 1.01, and we have two of those. We have two hydrogens, so we get about 14.03 grams per mole. Okay, so our empirical formula, we added up our molar mass, we get 14.03. Okay, but we're told in the problem that our molar mass is 56.1. Okay, you have to be given this extra piece of information to find the molecular formula. Okay, so now we're going to take our molar mass of our compound, what it should be, and we're going to divide it by what we got with our empirical formula. Okay, and we should get roughly 4. Okay, so this tells us that the molar mass is basically 4 times that what we have found. Okay, so what we're going to do is we're going to go back to our formula, which was CH2, and we're going to multiply all of our atoms by 4. Okay, so we get C4H8. It's butane. Actually butene. Okay, so now if you added up the molar mass of this, you would get about 56.1. Okay, so hopefully now you kind of see why it's a longer problem, worth quite a few points on the exam. So if you have to do both steps, ask for the molecular formula. If you can solve for the empirical formula, at least you can get that part correct. Okay, and then from that point, you have to be given the molar mass. So you go find that in your problem. You divide it by what the molar mass of the empirical formula that you found. Okay, once you see that you get whatever number you get here, whether it's 2, 3, 4, you multiply all the atoms by that number. And so you get C4H8 in this problem. Okay, do you have a question? Damien, do you have a question? 4 right here? Okay, it's kind of hard to see. Sorry about that. So you take, over here we found the molar mass of our empirical formula, okay, and we divide that into the molar mass of the compound. Okay, so we know our compound's actually much larger than what our empirical formula, and this equals 4. Yeah, sorry. It's hard to see that. I covered it up. There you go. Okay, and this, like I said, is what you'll do in the lab. You'll come up with and get your ratios and get your molecular formula. So, do this again. Okay, in your book it has a few other interpretations that we can use. This actually kind of bridges us into chapter 3, kind of the middle or end of chapter 3. So I encourage you to look at this, look over it. I'm going to go through it quickly, but majority of these type problems that are more than 2 or 3 steps or more than 2 steps we'll be getting from chapter 3, because that's really, but for this problem we're given grams of a compound. So we have ammonium phosphate. Okay, and we need to convert to mass of phosphorus. Okay, so what we're trying to find, we're going to have to go to moles and then to grams of just the phosphorus contained in the total compound. So we're just looking for the phosphorus here. Okay, so the first thing that we would do is convert from grams to moles. So I encourage you to do this at home. Be sure that when you add up the formula weight for this compound, okay, that you get 149.09. That's one of the most common mistakes the students do, is they assume they can do that because it seems easy, and then on the exam they get that part wrong, which messes up the whole rest of the calculation. Okay, so be sure that you understand how to come up with molar mass and formula weight. Okay, so the molar mass of this compound is here. So the first step is what we've been doing this whole chapter. So we just convert from grams to moles. Okay, and then this step is going to be a very important step come chapter 3, but we're going to be looking at a reaction, not just one single compound. Okay, and what we do, we know we have 1 mole in our numerator, so we've got to have 1 mole of our compound in the denominator. So that helps us know the sequence that we're going to go. And then this 1 mole here comes from looking at just this compound, and we have an understood 1 here. So we have 1 atom, which can also be written as 1 mole of phosphorus. So that's where this step comes from. Exactly. Yep. And then you'll see how, if you look back at this problem later when we're in chapter 3, you'll see how it's very similar to the problems in chapter 3. Okay, so now we have 1 mole of phosphorus in the numerator, so we have to have 1 mole in the denominator. And now we're just converting from moles to grams. Okay, and so we find this number here from our periodic table. And then if we multiply all the numbers on the top, multiply all of our numbers in the denominator, and divide the denominator into the numerator, we get 9.41 grams of phosphorus. Okay, so what that is telling us, that of this 45.3 grams of this ammonium phosphate, okay, 9.41 grams is phosphorus in that 45 grams. Okay, we often run into issues in the lab, and all of your reagent bottles will say, 99.9% pure, or sometimes they'll be 97% or 98%. Okay, and so we have to take this into account in our calculations, and this becomes really important if you have a really large-scale reaction, because if you have, hundreds of grams of a reagent, and it could mean that 20 grams of it, or 2 grams even, could be impurities. So we have to look at what's actually pure in our sample. Okay, and this becomes a huge issue in organic, in pharmaceutical companies, in industry. Anything that comes over the counter to you guys has like 0.0001 impurities in it. Okay, and so this is extremely, extremely important. Very, very hard to do. Trust me, it is not easy purifying compounds and getting it to the purity that we need it. In the lab, when we're using it to perform chemical reactions, not as big of a deal. But when it comes to your actual final product and what you're going to put on the market and things like that, it becomes very, very important. So how we find this is basically part over whole. You'll hear me say that a lot. And basically, you take the mass of just the pure substance from the sample over the mass of the sample. Okay, so this sample could include impurities as well. And then you times it by 100. And this gives you the percent purity. Okay, but how this is important to a chemist would be an example like this. Okay, so I go to the shelf and I pick up my sodium phosphate. Okay, and I read the label, and it tells me that it's 98.3% pure. And most of you are probably thinking, hey, that's pretty high. That's a pretty high percentage. Okay, and that is true. But if you're using a lot of this, so here even 250 grams is really not, I mean, it's a pretty large-scale reaction for academics, but not for industry. Okay, and so I want to know of that 250 grams, how much of it is pure sodium phosphate, and what is the rest? The rest of it is going to be impurities. Okay, and so my percentage, once again, whenever we see a percentage, this means it's out of 100, right? So we can say that 98.3 grams out of a 100-gram sample is pure. Okay, so if we have a 250-gram sample, and we can multiply, see my units cancel, our gram sample here we have 100, and we have 98.3 grams that's pure. Okay, and so we can cancel our units here. So we take what we're given. So here we're given that 250, and you multiply it times 98.3 over 100, and we get 246. So of that 250 grams, 246 is actually pure sodium phosphate. And this is also important because I need to know impurities aren't going to react in my reaction the way that I want them to. So I need to know exactly how much is pure that's going to react and do the chemical transformations that I'm expecting. Okay, and so when we look in Chapter 3, we're going to look at percent yields. Okay, you guys even did this. You're doing this in lab. It's a little premature to what you know, but you typically want a high percentage yield. Well, if you don't take into account your impurities, it's going to be lower than what you would expect. Okay, so 246, and then obviously we would have 4 grams of impurities if we take 250 minus 246. Okay. We're going to look at balancing equations now. So we're going to start Chapter 3. The calculations that you're doing in lab today will actually be covering on Monday. So for you guys that haven't had lab yet this week, I'll be kind of helping you, giving you the setup for the calculation, since it is a little bit early to give you guys the calculations till we get there. Okay, we're going to look now. Now we convert from grams to moles. We can convert from moles to grams of the same compound. Okay, we've looked at percent composition. We've looked at deriving the formulas. Okay, and then percent purity. Okay, now we're going to actually look at a chemical reaction. Okay, and this is what chemistry is all about. And you can study chemical reactions throughout the rest of chemistry, however long that you decide to stay in it. And so this is the very beginning. You have to understand what a chemical equation means, what reactants are, what products are, and then we have to learn how we can do calculations based upon the chemical equations. Okay, today we're just going to talk about a chemical equation, what it represents, and then we're going to look at balancing these equations. So a chemical reaction, I'm going to show a picture on the next page, but has reactants on the left side of the reaction, okay, and your products are going to be on the right side of the equation. And then you're going to see what are called stoichiometric coefficients. Okay, these are numbers that are relative amounts of each of the compounds involved, and it's the large number, okay, this whole number out here, that is in front. So these are coefficients that are out in front of the compound. Okay, and this gives you a relative amount. Okay, a chemical reaction, sometimes we get, especially in first semester, you're just going to try to balance them, you're going to try to do calculations with them, and it's often lost the sight of the fact that what's really going on here. Okay, so we've got, these are just kind of ball and stick models, but what's happening is these bonds here are going to have to break. They're going to have to rearrange, and they're going to have to react and form bonds with another compound to form the products. Okay, so there's a lot going on and a lot of Chem 2 and organic talks about, how is this really happening at the molecular level. Okay, but we all know, hopefully, that bonds are made of electrons, right? So that's really what's going on. So we're looking at electrons are being shared or they're transferred in some situations, and there's a rearrangement of electrons. Okay, so that's what's really going on. But these are our reactants here on the left side. Okay, these react. If you want to think of this arrow as writing to form, okay, reactants form, that's what this arrow means, products. Okay, so reactants and products, and these numbers here are coefficients. This reaction that I have up here is one that I require you guys to know, so you may want to start here. Methane and oxygen, so this is a combustion reaction, react to form CO2 plus water. This is one reaction that you guys will need to know. Okay, and you'll see how to balance it here in a few minutes. Okay, so if you see this symbol here, that's above this delta, that is for heat. That means that we're heating the reaction, so there are lots of reactions that include heating from some kind of external source. Okay, and so if we look at this, these are our reactants on the left side. If you want to think yields or forms, so our reaction arrow means these are our products here. Okay, if we look across, we're going to look at our coefficients. Okay, so we look out front, it's understood that we have one formula unit or 1 mole of iron 3 oxide. Okay? If you look at our carbon monoxide, we have 3 moles. That's what that 3 out front stands for. Okay, and then these are just the added up formula weights here. Okay, and then we have 2 atoms. Okay, we just have a single atom. We have iron here, which means we have 2 moles. Okay, and so this would be the molecular weight there, or formula weight. Okay, and then for CO2, we have 3 molecules of CO2, of carbon dioxide, and we have 3 moles. Okay, so that's what that number out front represents. Okay, so these numbers that we placed out front, you're going to have to learn to know what the number is or what the coefficient is in front of the reactants and the products. And we do this by balancing equations. Some of you probably did this in high school chemistry. Okay, but the reason that we do this is because of the law of conservation of matter. So this was something we discussed back in chapter 1, and that basically there is no detectable change of the composition of matter or the quantity of it in a chemical reaction. So basically you can't lose or gain matter or mass. Okay, so you have to have as many atoms, so you have to have the same number of each kind of atom on both sides of the equation. Okay, so if you have 12 carbons on the reactant side, you have to have 12 carbons on the product side. This reaction is propane burned in oxygen, so very similar to methane. They're both hydrocarbons, very similar to the reaction that you have to know. I want you to go through here and look and see how many carbon atoms, hydrogen atoms, oxygen atoms do you see on each side of the equation. Okay, and we'll answer this question in a minute. And then I want you to answer, is this equation balanced? Some students like to tally everything under here and said I've got 3 carbons and how many ever hydrogens and then Do the same over here. See if they match up. Mm-hmm. Okay, we'll talk about it. That's what I'm getting to. Okay, so how many people think it's balanced? Okay, how many don't think it's balanced? Okay, I know there's more of you too. Okay, this equation is balanced. Okay, but first you have to know how basically the kind of discrepancy for most students is knowing what to do with these coefficients here. Okay, so these coefficients are multiplied through times the atoms, the subscript that's on each atom. Okay, so here would be 10 oxygens. Okay, so this is obvious. We have 3 carbons, 8 hydrogens. Okay. Another thing that students, you may have the same atom in 2 different compounds. So you have an oxygen over here, oxygen over here. So you have to add those together. Okay, so here we just have an understood 1. So we have 3 carbons. And then we have 6 oxygens here. Okay, we have 8 hydrogens. Okay, but this 4 also multiplies through with this 1 here. So we have 4 more oxygens there. Okay, so if we tally this up here, so we've got 3 carbons on each side. Okay, we've got 8 hydrogens. We've got 4 times 2. We've got 8 on the product side. So remember, these are our reactants. These are our products. Okay. We've got 10 oxygens. Okay, and here we've got 6, 3 times 2, plus 4 times 1. Okay, so everything checks out there. So we have a balanced equation. Okay, this actually comes from your key terms handout, but I just felt like this is one of the more important parts for balancing equations. And we already stated that your equation must have the same number of atoms on each side. Okay, we've already discussed these numbers here are our coefficients. Okay, these are our subscripts. Okay, but what you're going to have to do is you're going to have to balance an equation. So you just looked at an equation and told me whether it was balanced or not. Okay, but you're actually going to have to balance this yourself. So I'm going to give you an unbalanced equation, and you have to balance it. So this right here, probably want to highlight this, and you'll be coming back to this probably while you're doing your homework. Okay, but to balance an equation, you can adjust the coefficient. Okay, you can change this number out front. Okay, so these numbers here. Okay, but you cannot change the subscripts. Okay. All right, if you change the subscripts, and believe me, a lot of students try to do this, you're changing the whole reaction. You're changing the compound in general. It's no longer water if you put H3O there. It's now hydronium, so it's not the same compound. Okay, so you can adjust these numbers out front. The sequence that I usually tell my students, because it works the best for most equations, is to balance everything other than hydrogen and oxygen first. Okay, so if you have carbons or metals or whatnot. Okay, and then balance your hydrogens, because usually these kind of go hand in hand with then balancing your oxygens. Okay, a lot of students, and I know I was one of those, I wanted the same way, a system to do balancing equations every single time. So if I started here, it always worked. Okay. Chemistry doesn't work like that. So there will be times that you will try to balance, things just don't work out. I encourage you just to erase it and start over. Okay, so it's not always going to be a perfect little system that works every single time. So it takes some thinking and some working through them. Some of them are very easy to do. Some of them not so easy. Okay, and once again, this is the same equation that I'm requiring you guys to know. Okay. So we'll do these two together. First two, and then I'll have you guys do a couple. Okay. We have carbon, hydrogen, and oxygen in our example. So we're going to have this also on our product side. And the first thing we're going to balance is our carbons. Okay, we're going to balance hydrogen and oxygen last. Okay, so if we look here, we've got 2 carbons on the reactant side. Okay, and so we need 2 carbons on the product side. Okay, so we cannot do this. We can't go in here and just go like this. Okay, so that would be definitely not the right answer. Okay, so we put a 2 here. Okay, but when you make that a 2, you've now also changed the number of oxygens that you have. Okay, so you have to be aware of that as well. Okay, but so far our carbons match up. We've got carbon, we've got 2. Okay. The next thing we're going to balance are the hydrogens. Okay, so we've got 6 on the reactant side. And so we only have hydrogen in one compound in our water there. So we've got to make it also 6. So what could our coefficient be here? 3. Exactly. Okay, and there'll be times you'll get all the way to this point, and then the last atom won't work. Okay, but this one does. Okay. Okay, so how many oxygen atoms do we have on the left side? 3. Okay, so, all right. Okay, and how many do we have on the product side right now? Okay, we've got to remember we've got 4 here, 2 times 4. We've got 4 plus 3, right? So we've got 7. Okay, so we've got 3 and 7, and we need these to match. So this is our higher number, so more than likely we can probably come over here. Okay, if we go and we do anything up here to our C2H6 oxygen, then we're going to change everything. We're going to change our carbons and our hydrogens too. Okay, so what do you think we could place in front of that oxygen there? A 3. Okay, so now we have 7 on both sides. Okay. This next example is one where I would definitely follow the tip of balancing everything besides hydrogen and oxygen first. If you try to balance the hydrogens and the oxygens first, you're going to start doing all kinds of changes, and there's really just one simple change that can be made. Okay, so we're going to start with, I also start for, if it's not hydrogen or oxygen, I start with whatever atom is listed first. Okay, so we've got rubidium there, so we have 1 on the left side and 2 on the product side, so we can do like so. Okay. Now let's look for our sulfurs. Do we need to make any changes? Okay, we've got 1 sulfur and 1 on the product side, so we're good there. Okay. Now we'll move to our hydrogens. Okay, how many hydrogens do we have on the reactant side? 2. Don't forget about your coefficient there. 2. And we have 2 on the product side. Okay. And oxygens, we have 2 times 1, so we have 2. And we also have 2 in our sulfur dioxide, so we have 3 oxygens. Oh, excuse me, we have 4 oxygens, and we have 4 over here. So all we had to do was make that one change, and it balanced everything else. So this is a perfect example of starting with everything other than carbon and hydrogen. Okay, so this would be the answers for those. Okay, this would be an example where that I might give you on exam. So I may give you the reaction, written out the balanced equation, or not the balanced equation, an unbalanced equation where it's written in the equation format. Or I can tell you what you're going to be writing out. So you have to write out the chemical equation. Okay, so you would take C7H16. Okay, I tell you that it burns in oxygen. So we talked about oxygen exists as O2, right? Because it's more stable. So you would say it burns in oxygen. Anything that's burning, if you want to be technical, we'd have that heat symbol there. And then it forms carbon dioxide. Okay, this is where you have to know your naming, and water. And that's one of the formulas that you have to know. Okay, and so now I want you to go through and balance it. Start with all atoms besides hydrogen and oxygen, and then hydrogen, then oxygen. Because oxygen always wants to make so it's diatomic, like all of your oxygen and chlorine, bromine, those are all diatomic molecules. Okay? Because they're electrons. If they are bonded to another oxygen, they have their full octet. So the Lewis structure of oxygen, if you want to. It'll look like that. You have a double bond in between, and both oxygens have 8 electrons around them, so they complete the octet rule. Do y'all need a couple more minutes? Do you have your answers? A couple more minutes? Okay. Okay, did everybody get this? Anybody not get this? Not have time to get this? All right. Okay, so we start with carbon. Okay, so we had 7 here. So we're going to place 7 on the product side. We have 16 hydrogens. So we're going to place an 8 here to give us 16 on the product side. We only have 2 oxygens on the reactant side, but we have 14 plus 8. So we have 22 oxygens on the product side. That looks like 220, but 22. Okay, so we have to go back over here and place an 11 there, because 11 times 2 equals 22. So we end up with 22 oxygens. Okay, I want you to try this one. Okay, and a hint, you're going to run into a little bit of an issue. So I want you guys to see what that issue is without me telling you. Okay, so you have NH3 burns in oxygen to form NO plus water. Oxygen's always diatomic because we talked about diatomic molecules. On the previous slide, I drew the Lewis structure. So oxygen wants to exist as O2 so that it has a full octet. You have a double bond and then the 2 lone pairs, so it has 8 electrons around it. Anybody running into a problem? What's your problem? Okay. Okay, you having trouble getting your coefficient on oxygen? Anybody? Okay. All right, so what happens here? Okay, so we look and we see that, so hopefully you guys got to this point. So you had a 2 there and a 3 here and a 2 here. Everybody get to that point? Okay. Okay, so we have 6 hydrogens on each side. We have 2 nitrogens on both sides. Okay, so how I got there, at first we start with just a 1-to-1, but then when we move over and we have to find a common basically multiple to get 6 over here, we then have to change our 2 there. Okay, and so once you change it there, so this is where it sometimes students get messed up. They'll change it here, but then they forget to go over and change it on the other side. Okay, so we have this. Okay, but how many oxygens do we have over on our product side? How many? We have 3. No, go away. What? Go away. Go away. Okay, we're going to go to the next. Okay, so we have 5 oxygens, but if we look here, now let's erase what I did. Okay, but we have 5 oxygens, but if we go over here, we have O2. Let me go get my pen back. I left my pen, hang on. Okay, looks like everything is crashing on me now. Okay, we'll just do this one on the board. Okay, so we get back. Okay, this is the last one anyways. Okay, so we have our, oh, that pen's not enough. Okay, so the answer is up here now, or not really, but kind of. Okay, so we get, okay, so we're at this point, and here. Okay, we're almost done. Sorry about the glitch here. Okay, we get to this point and we have 5 oxygens, okay, which we have an odd number. So we come over here and 2 times 2 is 4, and 3 times 2 is 6, right? So we can't get an odd number. We're never going to get there, okay? So what you can do is you write a fraction here, and then we double it, okay? Or you can just double it if you see it that way. So you write out the number that you need, okay? So you need 5 oxygens. You write that number up top, and you divide it by the 2. Okay, and basically what's happening is that 2 is canceling with this 2. Okay, but don't erase that 2. Okay?
The number at the bottom is
Yes, this is still a coefficient here. Yep, it's a fraction. Okay, so basically it's like 2.5. Okay, but typically, correctly, we don't ever put fractions really in our equations. We go ahead and get a whole number. So if you times the fraction by 2, you're going to get a whole number. So you just double everything. So if we double everything, we get a 4. Okay, and 5 halves times 2, that's where our 2 cancels there. Okay, and we get a 5, which is what we needed. And then we get a 4 and a 6. So we double our 2 and double the 3. Okay, so if you run into a situation where you cannot get an odd number, you're always going to get even, then you write out that number that you need over whatever it is here, the 2, and then double everything. Okay, so you'll have a few of those on your homework. Your chapter 2 and 3 practice, you can go ahead. There's only a few that we haven't gotten to yet, so you can go ahead and start balancing equations. There's quite a few of those. So go ahead and be working on that. Those of you that have a lab, be there at 1, and be sure you have on long pants and closed-toed shoes. Thank you. Yeah. Let me stop this one.